Welcome back to the American Ceramic Society's course on firing of ceramics. I'm Dennis Brosnan, and here we are in Unit 1 at class number 7. Now, this is the end of Unit 1. Before I get started, I want to say that we've explored the basic information from within the material that tells us what to do during firing. A while back, we started out with vitrified ceramics, and we learned that, of course, we just basically need to get temperature to activate the fluxes, create the glass, and soak long enough for enough glass to be formed for the ceramic to have the strength and the absorption characteristics that it needs to have. That's pretty well complicated by the fact that quartz is an impurity in most of our materials. And of course, then we have polymorphic transformations of quartz, alpha to beta quartz, for example. We have inversions of quartz, converting the quartz into other forms like tridymite and cristobalite. And those materials have their own inversions to deal with. But basically, it was pretty simple. From there, we went to firing porcelains. And there we had flint, clay, and feldspar as the main components. We were trying to reach a goal in the amount of glass that was formed. In hard porcelains, we had up to about 30% glass. In the previous example of earthenware, we only had a few percent of glass. So this made firing more difficult, and we had to use the formation of mullite, the aluminosilicate mineral mullite, that forms when we heat clays to a sufficient temperature, about 1,000 degrees Celsius, and form mullite. Further, the silica itself at the firing temperatures for these products is converted at least in part to cristobalite. And then we have, on cooling, the inversions of cristobalite and maybe quartz as well to deal with to avoid cracking, or it's called dutting, in those types of products. So firing porcelain is more difficult than firing the earthenware ceramics. Then last time, in the last lecture, we went to firing alumina materials. In the 90 to about 96% alumina area, we had an active liquid phase at elevated temperature, and we had mullite crystallizing within the interstices between the alumina or corundum particles that were there. Then we also considered the case of 99% alumina, and in that case, in order to use practical firing temperatures, we had to use different particle fractions of calcined alumina in the compositions in order to allow solid state sintering to take place. So today we're going to talk about firing cordierite, and we use this example because we have to meet an exact mix composition there. So the game's a little bit different in firing cordierite. And each one of these cases, you could have been interested in the detailed reactions that take place in new minerals that are formed and vitrification. Okay, if you didn't like that information, then you just really basically needed to learn that there are reasons internal to the material that we need to slow down during parts of sintering and need to avoid too much liquid formation. As you'll see in firing cordierite, you form a liquid pretty darn quick when you get up to the sintering temperatures, so you have to be very careful. So cordierite's a lot different material to make. Now, having said that, this is the end of Unit 1. We'll go into Unit 2 next time, which will be about kilns, furnaces, about supplying the energy that's necessary. That will be burner and burner control. And we'll consider all those things. So, you know, you may like that section better, Unit 2, which will be as long as this section. But you might have liked both sections. I can't tell. So let's go forward and let's talk about a diagram of magnesia, alumina, silica ceramics. So Professor Kingery is very good at this in plotting areas where compositions occur on a phase diagram. And if you look carefully, you can see that he has highlighted, he and his co-authors have highlighted areas of cordierite ceramics just in this area between magnesia, silica, and alumina. Okay, I'm used to silica being at the top of the diagram. It's got me a little bit confused when you put it down here, lower right, but nevertheless, he's also showing some magnesium silicate ceramics with a little bit of aluminum. These are sometimes called steatite ceramics, low loss ceramics that are used in electrical insulators. Over here, he's even shown feuchterite ceramics, magnesium silicate ceramics, which are used as refractory products in a lot of parts of the world. So we're only going to consider cordierite, and but there are other types of ceramics containing magnesia. Now, the reason that we like to talk about cordierite is it has a very low thermal expansion coefficient. Okay, thermal expansion coefficient is the slope of the thermal expansion line, thermal expansion in percent or unit dimension per degree of temperature. It's the slope of that line, and per degree Celsius, the thermal expansion coefficient of cordierite is pretty darn low. We use the Greek letter lowercase alpha to denote the thermal expansion coefficient, and you can see that it can be down around 1.8 times 10 to the minus 6 per degree Celsius. It's inches per inch per degree Celsius, or centimeters per centimeter per degree Celsius. Other ceramics like MgO are pretty high in thermal expansion, about 13.6 times 10 to the minus 6. I know it says times 10 to the plus 6 up here. That's what we multiplied this to make a whole number. Alumina around 8 to 9. Mullite, porcelain products, fire clay ceramics are in the area of 5 to 6. The cordierite has a very low thermal expansion coefficient. And the reason that's interesting is that the thermal shock resistance is inversely proportional to the thermal expansion coefficient. So if the thermal expansion coefficient is low, the thermal shock resistance is very high. When you heat and cool the ceramic, there's not much dimensional change, or not as much dimensional change, and that's what causes stress in thermal shock events. So cordierite ceramics are used where thermal shock resistance is really needed. Now, cordierite's a kind of interesting mineral, and so here's a little diagram of a hexagonal crystal of cordierite. It shows a seed crystalline direction and 2A crystalline directions. And so in 1974, it became known that in a couple of the A directions, thermal expansion coefficient was 2.97, but over in the other direction, it was minus 0.77. There was some other work that maybe made that a little more definitive later on. Here's a reference that you can look at if you're really interested in it. So what you're going to find out is that cordierite ceramics are typically extruded, and with plate-like kaolin crystals, the cordierite's going to grow on the kaolinite relics as you heat them. And if you orient enough kaolinite particles in extrusion, which is easy to do because they're flat plates and they like to align in the direction of extrusion, then you can get a very low thermal expansion coefficient. Now, you can't align them all because these are pretty quick extrusion processes, but if you align most of them, you'll be able to get the thermal expansion coefficient pretty low. So that's the central idea, is manufacture in such a way that we can get low thermal expansion coefficient. Okay, so let's approach this theoretically. That means that we're going to look at phase diagrams. And so here is a phase diagram arranged like I like it, with the MgO to the left. We've got alumina to the right and silica up here. So we've got various phases in here and various compatibility triangles. And you're going to find out that cordierite's right here. So it's going to turn out that if you're right on the money of the composition, and which, by the way, this has a little solid solution in here, and there are some cordierite polymorphs. One is called indiolite, the other cordierite. So nevertheless, but if you're right on the money of the composition, you're going to have 100% cordierite. But if you miss the composition a little bit, you can have mullite show up. You can have crystalline silica show up. You can have instatite show up. Forsterite show up. These are minerals over here in the magnesia silica phase diagram. You can have mullite show up, and you can then go down here and have magnesium aluminate or magnesia spinel show up. So the idea is going to be that if you hit this composition right on the money, you're going to be at the lowest thermal expansion coefficient. If you get off the composition a little bit, then you're going to have other minerals, and they're going to change the thermal expansion coefficient. For example, if we miss the composition and have a lot of free silica in the composition, that's going to be the highest possible thermal expansion coefficient. So generally, people that make cordierite like to be over here in the mullite cordierite area. Some of the newer technology suggests that you have reason that you might like to be in the magnesia spinel cordierite area. But you really don't want to be over here toward MgO or toward instatite or forsterite, or certainly free silica. So that's the deal. And I've blown this up a little bit. Cordierite is 2 moles of magnesia to 2 moles of alumina to 5 moles of silica. Okay, there's the line for cordierite composition right here. And that's where you want to be, right in the middle of that circle, right on that line of solid solution. If not, you're going to be in the compatibility triangle with cordierite and mullite and silica, or one of these other compatibility triangles. The other one down here is going to be cordierite, alumina, magnesium aluminate. So those are your choices. So let's just figure out what's happening. And we've just been to these particular diagrams. Let's go forward. Now, cordierite occurs naturally, but not in large scale deposits as a mineral. So typically we have to make cordierite. The high purity cordierite is made by taking mixtures of talc, which is magnesium silicate represented over here on the phase diagram. And we're going to take metakaolin here. Remember, that's dehydroxylated kaolin. And we're going to try to hit that composition. And you're going to find out that you have to add a little bit of alumina to hit that composition. You can't quite make the required alumina content with talc and metakaolin alone. You're going to have to sweeten it up with a little bit of alumina to hit that composition. Now, here are sections of the 3-component diagram, and I like to look at these because they are pretty easy to look at. Here we've got cordierite. You can see a paratectic here. So once you heat above the point at liquid forms, above the paratectic temperature, you'll have a solid phase plus a fair amount of liquid immediately. So generally in the older technology, you didn't want to go above that paratectic unless you had played some games with the composition, because you'd have all of a sudden too much liquid and you would have indeed begin to have some melting in the ceramic. If you get off the composition a little bit, you're going to see some pretty low melting temperatures down around 1350. The paratectic temperature is here above 1450 or thereabouts. So you really got to worry about these temperatures down here. Remember that I've tried to teach you that in firing a ceramic, the first liquid that's going to be formed is the lowest eutectic in the system. Even though the composition might not suggest that, the overall composition, you can form that liquid. Now, as you continue firing, that liquid composition will gradually go toward the overall composition, toward cordierite, and disappear. This is what reactive centering is all about. So keep in mind 1350 and up here above 1450 where we get up to the paratectic temperature. Now, I decided to melt some cordierite. The blue line is a differential scanning calorimetry curve of what happens to cordierite in a crucible when you try to melt it. And right over here at 1305 degrees C, the cordierite that I had made, the computer identifies that as an inflection point. Okay, and it's pretty interesting that it shows an endotherm. Of course, melting is endothermic pretty quickly until we get up here close to 1400 degrees C, and all of a sudden we're at the paratectic temperature. Now this specimen was a little bit impure, and that's why these temperatures are a little bit lower than those indicated by the phase diagram. But what I'm trying to say is we begin to get melting at 1305 and melting in abundance at 1389 degrees here. And of course, the specimen melted entirely and then solidified. Please ignore the blue line because I was playing some games with some fluxes at that particular time. So 1355 in the pure system, but we're going to get melting temperatures below that in the real world. Okay, well, let's look at technical cordierite. Understands what's out there in the literature, what we can glean from that in the literature. And I like to point you to Latchman's patent. Now, this is an old patent, 1975, but it is a wonderful patent. And so in this patent, Latchman says that he's talking about making extruded cordierite. You can have a thermal expansion coefficient as low as 5.5 times 10 to the minus 7. That's about 0.55 times 10 to the minus 6. In the range 25 to 1000 degrees Celsius. So you can find this patent on uspto.gov. Just key in the number and you'll get the patent and you'll be able to read it. And of course it is written in lawyer speak, but nevertheless, it's worth the read. So here's some diagrams from Latchman's patent. His figure 1 shows a typical honeycomb ceramic. Okay, so you can see it has an axis of symmetry in the long direction, typical of an extruded product, and it has open cells in here. Of course, these fire devices are used in automotive catalyst carriers, and so they're used to clean up the exhaust gases in your car, particularly to get rid of hydrocarbons and carbon monoxide. So they're extruded, and his figure 2 shows a diagram of a square cell in this particular case. He's trying to illustrate that we get different coefficient of thermal expansion, CTE values, in different directions. The one that's the most important is in the direction of the extrusion, in the long direction of the device. Okay. For reasons which will become clear a little bit later on, we can deal with some cracking or walls cracks within the walls of the cells, but we don't want it to crack longitudinally and fall apart. Then the device wouldn't be workable at all. So how was Latchman able to do this? He said that within any individual cell wall, because we're extruding this, the kaolin crystals, which are plate-like in nature, are going to line up. So their basal plane is aligned parallel to the direction of extrusion. So this is a wonderful idea. And it would be great if we could get all of them to line up in the direction of extrusion. We can't do that because we have different particle sizes and we don't reach a dynamic equilibrium in extruding a small article. But nevertheless, this particular alignment of kaolin crystals is important because the end result is going to be is the cordierite crystals are going to grow on top of these residual platelets. And if they line up so their low expansion direction is in this direction, on the average, then we're going to have low expansion coefficients in the device that we fire. Wonderful patent. Now, this may be hard for you to see. I hope not. Hard for me to see. But theoretical cordierite, you can see alumina about alumina 34.7. These commercial cordierite products, I see 32, 33, 32. Silica is 51.4. Well, I see 49.9, 49.3, 49. And last but not least, MgO 13.7. Here's MgO down here. 16 and this particular one, 16, that one, 17, and that one. So these are pretty close to the cordierite composition. And so let's look at the thermal expansion and the X-ray diffraction. And one of these cordierites, commercial cordierites, like the type of cordierite that Latchman was making, the phases were identified by X-ray diffraction. Remember that identifies the minerals. The phases were identified as cordierite and mullite. Of course, if there's glass present, amorphous phase present, it's not going to identify that. Well, here's the thermal expansion coefficient, starting out with 0% expansion and heating up. Notice it didn't go up uniformly. All of a sudden it went down. The thermal expansion coefficient was negative. The reason for that is the anisotropic expansion of the cordierite crystals. So if you line up these crystals that you've created in firing of the talc, clay, and aluminum mixtures, then you'll get a dip in the thermal expansion on heating. And then in this particular cordierite, we had an inflection point of 1364, about 1365 degrees Celsius, and that's getting pretty close to the peritectic temperature. So that's where approximately this product was probably fired in this example. The honeycomb products come in different shapes and sizes and all have open cells for the gases to flow through whatever gas is being cleaned up. Automotive exhaust or other industrial gases can be cleaned up with these types of products. And typically in the smaller products, we'll have 400 cells per inch, and the wall thickness can be down here about 0.17 millimeters. That's 170 microns up to about 0.23, 230 microns. 170 microns means that the wall is approximately 170 particle diameter thick. So that's not a very great thickness. So some of the thinner ceramics that I've been involved with. Now, of course, Latchman's patent was pretty old, and here's a 2011 patent. And in that patent, a specified pore size distribution is given. a certain firing strategy is given to get us above the peritactic temperature briefly and then cool off. Okay, and maintain a certain temperature for a period of time. I don't know if you want to believe these hours of soak or not, but you might. That's up to you. So nevertheless, this was an interesting patent. Now, the fact that these guys have gone up with this little blip suggests to me they could have intentionally gone off the Cordy-Wright stoichiometry. They might have added a little extra alumina to this composition. They were trying to control the pore size distribution and attain a certain porosity. Well, one way to attain a certain pore size distribution is to allow alumina spinel to be formed in the production of Cordy-Wright. That's going to be a little bit of an expansion reaction, and also kind of serve as a framework in the body to kind of hold things together. So whether they were doing that or not, I don't know, but you can see there has been evolution in this technology. This was another Corning patent. I'll say to you that in my lifetime of experience as a ceramic engineer, this work with Cordy-Wright's been some of the best ceramic engineering I've ever seen. I mean, this has been fantastic work. I've seen some great work in refractories, don't get me wrong, but this work in Cordy-Wright has been really phenomenal. Okay, well, we'll go to laboratory production of Cordy-Wright. And, you know, I really like to use the Cordy-Wright example in teaching in ceramic engineering courses because it allows you to tie everything together. Chemistry is in X-ray fluorescence analysis, mineralogical analysis, X-ray diffraction, and physical properties, in this case, thermal expansion. So I use Cordy-Wright a lot. I don't consider myself an expert at making Cordy-Wright, but it was a really good class example because I was able to use cheap labor, in other words, students, to make samples in laboratory exercises, and then they could use the laboratory instruments to figure out what the composition was. Did they meet the compositional goal for making Cordy-Wright? What the mineralogy was? Did they meet the mineralogy goal? What the thermal expansion was, which is, of course, a very important product attribute. Now, in making Cordy-Wright, there are two approaches. Approach A was to take magnesium oxide as a reactant and add it to clay. Okay, that's a very old technology, and you will make semi-Cordy-Wrights that way. I'm going to show you some laboratory data where waste Cordy-Wright was used from saggers in ceramic production. This material was ground up and added to clay, and some objects were formed. So in this particular case, instead of 13.7% MgO, they only had about 3% MgO overall in the product that was made. They had about 34.7 alumina in theoretical Cordy-Wright, and you can see they got above 40 here in alumina. So they mixed clay, fire clay, and Cordy-Wright aggregate, Cordy-Wright powder from waste sources in making this particular semi-Cordy-Wright in example A. So anyway, if you took the powder itself, a formed object from the powder, and check the thermal expansion, it's going to shrink a little bit as you get to fairly low temperature when some of the binder decomposes. Get up to dehydroxylation, it's going to lose shape again, lose some expansion again. So this is not a good way to evaluate that. If you heat it up in soak to elevated temperature, as I did here, and then heat and cool it off, we have reversible thermal expansion. And we got about 6.7 times 10 to the minus 6 and thermal expansion coefficient. Well, that's pretty darn high. The reason it's high is that the semi-chlorites that were made in this example contain a lot of mullite. So the thermal expansion coefficient of the article that's been made is more similar to mullite than it's chlorite. It's pretty high, 6 to 7. You know, that's pretty darn high. So they don't contain very much chlorite, but they contain a bit of chlorite. So there we go. That's one way to make it. The more interesting way is to make high purity chlorite. Then you use kaolin, aluminum silicate, talc, magnesium silicate. And as I've said before, you have to sweeten it up with a little bit of alumina to hit your compositional goals. So this is the way that we make high purity chlorite. Kingery and others have told us a little bit about what happens when you begin to, when you form the article, a mixture of clay talc and alumina together. You've added binders, plasticizers, so you're going to extrude non-plastics, so you have to add these things. And you've piston extruded them or used an auger, maybe a twin screw auger, to extrude them through a very complicated die arrangement to create that geometry of the filter, the catalyst reactor support. And what happens is you got to remove those binders, and that requires probably 400 degrees C and higher to get rid of them. Remember, we want to get them out before we form any kind of liquids. We're going to dehydroxylate the clay, you know, up in the area of 500 to 600 degrees C. We're going to dehydroxylate the talc. It has a fairly broad endotherm for dehydroxylation, but up around 900 to 910 degrees Celsius. We can form some initial and perhaps transient liquids. And that always happens above about 1,000 degrees C. We can form some mullite. We're going to form chlorite crystals on the kaolin relics that are there. We can get partial melting going up to the paratectic. We can get secondary reactions if there's additional alumina added, for example, or some other substance. And we're going to get pore consolidation and growth. So a lot of stuff happening when we make this material chlorite. Now, very quickly, here's a data sheet for a talc. I don't believe this talc is currently commercially available, but you can see that it contains magnesium oxide, about 31%. It contains silicon dioxide as this other major constituent. So it's a magnesium silicate mineral. Talc occurs naturally, of course, in the world in various deposits. It's ground sized to reach certain particle size distributions as shown over here. One very important thing to mention is that talc has a Wilson ignition of around 5.5%. And we're going to mix it with clay, and you've already seen this data sheet, catalyst grade kaolin. I don't believe it's commercially available now. That's what I used in my laboratory experiments. It has a Wilson ignition of about 14.8%. That's important to know, and we're going to add it to calcined alumina. You've seen this data sheet from the last class, and Wilson ignition is nil, negligible for that. Each one of these materials has an X-ray diffraction pattern, of course. And of course, kaolin usually brings some quartz along with it. That's the quartz down here. And the kaolinite peaks are given right there. Calcined alumina is nothing but corundum, aluminum oxide. That's what the X-ray diffraction has identified. Okay, Now we're going to go forward. You got to batch this together. You got to make a batch calculation. So you've got a goal of a certain amount of magnesia, a certain amount of alumina, a certain amount of silica, and we've got a chemistry with a loss on ignition. That's supposed to read LOI 14.8%, talc 5.5%, and alumina none. So to meet this composition on a calcined basis, we have to start with a kaolin composition on a calcined basis. So the composition without any loss of ignition. We'll start with a talc on a calcined basis. And we'll mix alumina, calcined talc, and calcined kaolin together in certain proportions to get that composition. Once we have that composition, then we have to go back to an as received weight basis and divide the kaolin by its residual before ignition and the talc by its residual before ignition. And then we'll add all those up and normalize them to 100%. And we've got our batch. In other words, we cannot batch based on the as received weight basis. We've got to convert to calcined basis, meet the composition, and then reconvert to an as received weight basis. You can do this manually. You can do it with Excel. There's a matrix method with Excel that makes this pretty simple. Now, batch calculations are used in making glasses and enamels and glazes and things of this nature. But they're important in certainly making cordierite and other ceramics. So I taught people batch calculations in detail in my academic courses because I thought it's important for them to see it somewhere. So I didn't think the rocket scientists on the faculty were covering this material. So I did. So I'm sitting at a coffee shop one day in a small town, not where I live, and I'm sitting there and drinking some coffee with my wife, and a guy walks up to me. I didn't recognize him, but he said, "Are you Dr. Brosnan?" I said, "Yeah." And he said, "Well, I had you for ceramic engineering." I said, "Well, good." And I said, "I hope it did you some good." And he said, "Well, guess what I'm doing now? I'm doing batch calculations for a glass plant. I have to get the raw materials and I have to do a batch calculation to make sure the composition is on the money so we make the right glass product. So I'm using exactly what you taught me." And I thought, well, gee, that's pretty good. I helped somebody make a living. That's good. So after we batch it, we have to mix it up and we have to do a good job of mixing. I can't spend the time on more on batch calculations. That's something others should have done in this ceramic sequence. So typically we're going to use a piston type extruder to make this product. At least that's the way it was in the beginning. So we drop a batch in a cylinder. That cylinder rotates down. There's a piston that's going to push that material forward. All this, once it's folded down, is horizontal, and it pushes out the cordierite onto a tray here. Tray is necessary because the grain strength is not good when this product is made. People today use twin screw augers and continuous extrusion to make this product. That's revealed in some of the patents. People are not using piston extruders in production all the time. We did some piston extrusions with cordierite, and we did them with fast travel of the piston, and we measured the force that was required to make the material move. Okay, and so we also extruded more slowly, and we made the force, we measured the force to extrude. The force was always lower with the lubricant present, and so that was part of the reason, trying to show the students what we were accomplishing by adding the lubricants to the system of powders and with the binders. Now, I did this over a number of years, and we came up with various talc, clay, kaolin mixes. Sometimes we used MgO powder in some of the mixes with some kaolin, trying to meet the composition on the money. We fired the composition up to about 1350. In some cases, we melted the compositions. We got thermal expansion coefficients down here as low as 2 in the direction that we were making the samples, trying to align the clay particles. Now, I couldn't make these all the time by extrusion, so sometimes we did plastic pressing, and we would, if we pressed a pellet by plastic pressing, that's high liquid content pressing, and that would align clay particles away from the axis of the pellet that we were pressing. Well, that's what we attempted to do because I didn't have a piston extruder. Just to mention, we also did some glycerin burnout curves just to try to see what was happening at the low temperature region. So you can see that glycerin was coming out likely over a range of temperatures due to depolymerization up to about 1,000 degrees. So some of these complex binders take a while to remove by evaporation, depolymerization, or oxidation. Some of the trial batches that we made, typically densities were in the range of 2.1 to 2.15, and the dried densities, fired densities were around 1.8 to 1.9. Firing shrinkages, I guess it'd be good for you to see the whole slide here. Firing shrinkages were average minus 0.35, minus 0.75 in our laboratory firing process, which didn't fire them as hard as probably commercial ceramics would ever be fired. But remember that there are expansion reactions taking place along with shrinkages. Loss on ignition average was around 12%, perhaps 11% here. So that's some typical laboratory data. When we fired these materials, and I used typically a class split into group A, B, and C. We formed cordierite. We might have other materials left over, like magnesium silicates and magnesium aluminum silicates in the fired product. Another group had cordierite, and so we had some corundum left over in the fired product. So we didn't convert all of our material to cordierite, even though theoretically we were pretty close to the composition on the money. So remember, part of the lessons here have been that the phase equilibrium diagrams show us the direction. So some of the best cordierite we made is shown here. Thermal expansion, delta L over L0 expressed as a percent. Change in length per unit length expressed as a percent versus temperature on heating. The fired cordierite went negative. So obviously we were able to get a little bit of clay alignment. The thermal expansion coefficient was 2.35 in the low temperature region of room temperature up to about 300 degrees C, 600 degrees C, up to 600 degrees C, it was 2.9. So we were down around 2 in thermal expansion coefficient. Not as good as commercial cordierite, but pretty good. We had a pore size distribution. The peak in pore sizes here was in the area of 1 to 10 to 20 microns or thereabouts, about as big as some of the kaolin crystals, kaolin particles that were present. So that was, I have to correct this. This is not cordierite that we made. This is cordierite that was commercially made. So pretty much a unimodal 4-size distribution in commercial cordierite. Here's cordierite that we made, and they're polished sections on a microscope. This is at very low magnification and reflected light. The black holes, which are mostly spherical here, are pores. So the cordierite's pretty porous that we made, and interestingly enough, the pores are reasonably spherical, which means that we had a fairly fluid liquid phase present at the firing temperature for these ceramics. So all the groups produce this kind of microstructure. Some detail of one of the groups, which there's their composition here. In X-ray diffraction, we found cordierite, some cristobalite, which is not visible in the picture, or tridymite. Corundum is probably the lighter phase that's standing up here because of its hardness. In this polished section, we can see it. And cordierite and forsterite is down here in the background. The cordierite is probably the lighter gray phase, very typical of forsterite, magnesium silicate with cordierite in the continuum with some glass present, and pretty good thermal expansion coefficient. So in order to figure out these phases exactly, I would revert to scanning electron microscopy, but nevertheless, you can see the rounded pores here. Sometimes they're elongated in this microstructure. Now there's some additional reading other than what I've told you about. There are a couple of cordierite patents here that are pretty darn interesting. The top one here is mostly about some of the binder systems that were used. You can look at the examples in the patents and read the patents. It's tedious to read patents, but you can read them and get an idea of what people are thinking. You don't know their exact compositions. They're not going to give you every one of their secrets, but they're trying to protect their technology. And this one here, they're developing cordierite with very narrow 4-size distributions, and I believe they were actually adding some magnesia, some excess alumina in the composition to reach those narrow size distributions. Now, when cordierite first came out as a catalyst support, the catalyst support was fired, and then you put a wash coat of porous alumina on the surface to accept the catalyst. And that was fired on. My impression is that cordierite may have evolved in production to where you eliminate that second handling operation and can make a porous enough ceramic to accept the catalyst and to accomplish any filtration that you want without having to go through a two-step process. One thing you need to do after firing this is add the catalyst itself to it, and the catalyst is usually palladium and platinum. Now, if you want to, you can also access this reference on the web. It gives some useful information. It's back to 2003, so it's a pretty old article, but nevertheless, it argues that you can use different qualities of talc in making cordierite other than some of the ones that I showed you today. I believe that the author worked for a French talc company, Luzenac. So you also can read some more in the Journal of American Ceramics Society about anisotropic thermal expansion of cordierite crystals. So you got a whole lot of information there that you could look at. Let's give a summary. So we explored semi-cordierite and high purity cordierite. High purity cordierite was the more interesting one for us. We used talc, kaolin, alumina mixes to meet the compositional goal. we talked about the mineralogical reactions on heating, and particularly we talked about the periotic temperature being around 1355. So in traditional quarry-wright, you have to be careful not to exceed that temperature unless you've done something to influence the amount of glass phase present. Otherwise, you can get deformation of your wear. So I believe that some people have gone to non-stoichiometric compositions on purpose to control some of the properties. Now, there was a slide earlier. I don't know if I talked about it or not, but it was about intentional efforts to make non-stoichiometric quartz in my laboratory, just to demonstrate to students what happened to thermal expansion coefficients. And if you saw that slide, you might have seen some melting or generally higher thermal expansion when some of the higher expansion constituents existed as discrete phases in the fired quarry-wright. So this is the essence of Unit 1 classes. About vitrified ceramics, earthenware, about porcelain, about alumina ceramics, and about quarry-wright. The reactions take place. These require energy or temperature to take place, and they take time. So there's thermodynamics and kinetics involved in here. We're approaching equilibrium. We rarely get there. Centering takes place through vitrification in the simplest case, through reactive centering in some cases, and solid state centering. So the bottom line is that an older term that you use, control rate centering, in firing these products, you always slow down the heating and cooling schedules whenever a volume transition takes place. You give the ceramic time to go through those transformations in the firing schedule so that you don't cause cracking, either through expansions or contractions that take place too fast. That's the bottom line of Unit 1 here that we've had in the course. We're going on to Unit 2. So that's great. Unit 2 is going to be about kills and firing. So if you haven't done it, you can look at the downloads. The thermal ceramics download is the K calculator, thermal conductivity calculator. I've had some trouble since this went to the Morgan website to make it work, but I still have older models on my computer. Honeywell bought the company Halk Combustion that made this program eSolutions. So I'm absolutely sure you can download eSolutions on easily on your computer. But if you can't get the thermal conductivity calculator, don't worry about it, because in fact the Honeywell program will do the same thing. So I hope you've enjoyed today's class. And just to be more practical, when we get into talking about combustion and insulated boxes, we call kilns and furnaces. So we're going to talk about that in at least 7 or 8 lectures next time, and in the next unit. So we get started next time. Remember that you can always make an appointment with me, have Zoom office hours, or you can email me with any questions that you have. So I'll look forward to next time.